NENOMATICA, where mathematics meets YouTube excellence. The second law of power. Welcome to today's math lesson. We'll explore an important property of powers and exponents. Specifically, we'll prove the rule for multiplying numbers with the same exponent. The key theorem we'll prove today is that when we have two numbers a and b raised to the same power, m, the product equals the product of the bases raised to that power. In mathematical notation, this says, for all real numbers a and b, and for any integer m, a to the power m times b to the power m equals the quantity a times b, all raised to the power m. Let's prove this theorem step by step. We start with the left side of the equation, a to the power m times b to the power m. First, let's expand what these exponents mean. Remember that a to the power m means multiplying a by itself m times. So a to the power m can be written as a times a repeated m times. Similarly, b to the power m means b times b repeated m times. Now, we can rearrange these terms using the commutative and associative properties of multiplication. We can pair each a with ab to create m pairs of a times b. We now have the product a times b repeated m times. By the definition of exponents, this is exactly the quantity a times b all raised to the power m. Therefore, we've proven that a to the power m times b to the power m equals the quantity a times b all raised to the power m. Let's understand this proof with some color coding. The blue terms show a repeated m times, the red terms show b repeated m times, and the green terms show the product a times b repeated m times. Welcome to our lesson on powers and exponents. Today, we'll be looking at various examples of how to work with exponents and discover some important patterns that will help us simplify complex expressions. Let's start with our first example, 4 cubed times 5 cubed. According to our first step, we can rewrite this as open parentheses, 4 times 5 close parentheses cubed. This is because when we multiply expressions with the same exponents, we can group the bases and keep the exponent the same. Next, we multiply inside the parentheses to get 20 cubed. This is the final form for this expression, which represents 20 cubed. In our second example, we have 1/2 to the power of 4 times 5 to the power of 4. First, we can use the same rule as before, rewriting this as open parentheses, 1/2 times 5 close parentheses to the power of 4. Next, we multiply inside the parentheses. 1/2 times 5 equals 5/2, or 2.5. So we have the fraction 5 over 2 to the 4th power, which is our answer. Moving to our third example, we have 2 cubed times 3 cubed. Applying our rule, we can rewrite this as open parentheses 2 times 3 close parentheses cubed. Then, multiplying inside the parentheses gives us 6 cubed. This gives us our final answer, 6 cubed. For the fourth example, we have 1 to the 5th power times 2 to the 5th power times 3 to the 5th power. First, we'll use our rule to group these terms as open parentheses, 1 times 2 times 3 close parentheses to the 5th power. Multiplying inside the parentheses, we get 6 to the 5th power. And in the final step, we simplify to get 6 to the 5th power, which is our answer. Now let's look at our fifth example, which introduces variables. A to the 5th power times b to the 6th power times a to the 4th power times b to the 3rd power. First, we'll group like terms. We have a to the 5th power times a to the 4th power, and b to the 6th power times b to the 3rd power. Next, we can add the exponents of like terms. So a to the 5th power times a to the 4th power equals a to the 9th power, and b to the 6th power times b to the 3rd power equals b to the 9th power. So we have a to the 9th power times b to the 9th power. Finally, using our earlier rule, we can write this as open parentheses, a times b close parentheses to the 9th power, which is our answer. For our final example, we have a to the 40th power times b to the 20th power times a to the 20th power times b to the 25th power times b to the 15th power. First, let's group like terms. We have a to the 40th power times a to the 20th power and b to the 20th power times b to the 25th power times b to the 15th power. Next, we add the exponents for like bases. A to the 40th power times a to the 20th power equals a to the 60th power. and b to the 20th power times b to the 25th power times b to the 15th power equals b to the 60th power. So we get a to the 60th power times b to the 60th power. Finally, we can rewrite this as open parentheses, a times b close parentheses to the 60th power, which is our final answer. Our first example is a times b times a squared times b squared times a cubed times b cubed times a to the power of 4 times b to the power of 4. To simplify this expression, we'll group the terms with the same base together. First, let's rearrange this as a to the power of 1 times a squared times a cubed times a to the power of 4, multiplied by b to the power of 1 times b squared times b cubed times b to the power of 4. Now, using the product rule for exponents, when we multiply powers with the same base, we add the exponents. So this becomes a to the power of 1 plus 2 plus 3 plus 4 times b to the power of 1 plus 2 plus 3 plus 4. Adding these exponents, we get a to the power of 10 times b to the power of 10. Now we can rewrite this as the product a times b all raised to the power of 10. 8 to the power of 11 times the fraction 5 over 8 to the power of 11. Using the product rule for exponents, we can rewrite this as the product inside parentheses, 8 times 5 over 8, all raised to the power of 11. Simplifying the expression inside the parentheses, we get 5 to the power of 11, is the fraction 2 over 3 to the power of 8 times 6 to the power of 8 times 2 to the power of 8. First, using the product rule, we can combine everything under one exponent as the product of 2 over 3 times 6 times 2, all raised to the power of 8. Simplifying the expression inside the parentheses, we multiply the numerators. 2 times 6 times 2 equals 24. So we have 24 over 3, all raised to the power of 8. Further simplifying, 24 over 3 equals 8. So our final answer is 8 to the power of 8, 0.04 times 5 squared. First, let's convert 0.04 to a fraction. 0.04 is equal to 4 over 100. We can simplify 4 over 100 to 1 over 25. Since 25 is 5 squared, we can rewrite this as 1 over 5 squared. So our expression becomes 5 squared over 5 squared. This can be rewritten as the fraction 5 over 5, all squared. 5 over 5 equals 1, so we have 1 squared. And 1 squared is just 1. Our fifth example is 2 cubed to the power of 5 times 3 to the power of 5, all cubed times 6 to the power of 15. First, let's simplify the nested exponents. 2 cubed to the power of 5 equals 2 to the power of 15, because when we have a power raised to another power, we multiply the exponents. 3 times 5 equals 15. Similarly, 3 to the power of 5, all cubed, is equal to 3 to the power of 15, because 5 times 3 equals 15. So far, we have 2 to the power of 15 times 3 to the power of 15 times 6 to the power of 15. Now, we need to recall that 6 equals 2 times 3. So 6 to the power of 15 is equal to 2 to the power of 15 times 3 to the power of 15. So our expression is now 2 to the power of 15 times 3 to the power of 15 times 2 to the power of 15 times 3 to the power of 15. Grouping like terms, we get 2 to the power of 15 times 2 to the power of 15 times 3 to the power of 15 times 3 to the power of 15. Using the product rule, this is equal to 2 to the power of 30 times 3 to the power of 30. Finally, using the definition of 6, we can say this simplifies to 6 to the power of 30. Welcome to this math tutorial, where we'll solve a problem about counting digits. Let's see how many digits are in the number, where a is defined as 5 to the power of 104 multiplied by 4 to the power of 52. Let's begin by rewriting the expression for a. First, we can express 4 as 2 squared. So 4 to the power of 52 becomes the quantity 2 squared, all to the power of 52. Now we'll apply the power to power property, which states that when we have a power raised to another power, we multiply the exponents. So 2 squared to the power of 52 becomes 2 to the power of 2 times 52, which is 2 to the power of 104. At this point, we have a equals 5 to the power of 104 multiplied by 2 to the power of 104. We notice both bases are raised to the same exponent, 104. When we multiply quantities with the same exponent, we can use the product rule of exponents. The product of powers with the same exponent equals the product of the bases raised to that exponent. So we get a equals 5 times 2, all raised to the power of 104. The next step is to simplify what's inside the parentheses. 5 times 2 equals 10. So we have a equals 10 to the power of 104. Now that we have a equals 10 to the power of 104, we can determine how many digits this number has. There's a useful property. A number of the form 10 to the power of n has n plus 1 digits. This is because 10 to the power of n is a 1 followed by n zeros. So 10 to the power of 104 has 105 digits. Therefore, our answer is that a is a 105-digit number. Welcome to our math lesson on comparing expressions with exponents. Today we'll learn how to compare numbers in exponential form by expressing them in a way that makes comparison easier. Let's look at our example problem. We need to compare the following numbers: 25 cubed, 2 to the 12th power, and 36 cubed. We need to determine which one is the largest and which one is the smallest. When comparing expressions with different bases and exponents, it's often helpful to convert them to a form where we can make a direct comparison. In this case, let's try to express each number in a form with the same exponent. Let's rewrite each number as a power with the same exponent. First, 25 cubed. We know that 25 equals 5 squared. So 25 cubed is the same as 5 squared cubed. Using the power of a power rule, we can multiply the exponents. So this equals 5 to the 6th power. Next, for 2 to the 12th power, we can rewrite it as 2 squared to the 6th power. 2 squared equals 4. So this is 4 to the 6th power. Finally, for 36 cubed, 36 is 6 squared. So 36 cubed is 6 squared cubed, which equals 6 to the 6th power. Now we have each number expressed as something to the 6th power. 5 to the 6th, 4 to the 6th, and 6 to the 6th. Since all have the same exponent, we only need to compare the bases. Since 4 is less than 5, and 5 is less than 6, we can conclude that 4 to the 6th is less than 5 to the 6th, which is less than 6 to the 6th. Translating this back to our original expressions, we can say that 2 to the 12th is less than 25 cubed, which is less than 36 cubed. So our final answer is 2 to the 12th is less than 25 cubed, which is less than 36 cubed. Today we're going to solve a fascinating number theory problem involving very large powers. Let's look at our problem. If 2 to the power of 1402 is an m-digit number, and 5 to the power of 1402 is an n-digit number, we need to find the value of m plus n. First, let's recall an important property about the number of digits in a positive integer. If a is an n-digit number, then a is greater than 10 to the power of n minus 1, and less than 10 to the power of n. For example, 13 is a 2-digit number, which means it's greater than 10 to the power of 1, and less than 10 to the power of 2. In other words, 13 is greater than 10, but less than 100. Similarly, 130 is a 3-digit number, which means it's greater than 10 to the power of 2, and less than 10 to the power of 3. So 130 is greater than 100, but less than 1,000. Now, let's apply this property to our problem. Since 2 to the power of 1402 is an m-digit number, we can write that it's greater than 10 to the power of m minus 1 and less than 10 to the power of m. Similarly, since 5 to the power of 1402 is an n-digit number, we can write that it's greater than 10 to the power of n minus 1 and less than 10 to the power of n. In the above exercise, we multiply both sides of the inequalities. When we multiply two positive inequalities, the result is still a valid inequality. So, multiplying the two inequalities gives us 10 to the power of m plus n minus 2 is less than 2 to the power of 1402 times 5 to the power of 1402, which is less than 10 to the power of m plus n. Now, let's look at the middle expression. 2 to the power of 1402 times 5 to the power of 1402. Using the rule for products of powers with the same exponent, we can rewrite this as 2 times 5, all raised to the power of 1402. 2 times 5 is 10. So this simplifies to 10 to the power of 1402. Now that we've simplified the middle expression, let's substitute this back into our inequality. We get 10 to the power of m plus n minus 2 is less than 10 to the power of 1402, which is less than 10 to the power of m plus n. Now, for powers with the same base, we can directly compare the exponents. So from our inequality, we can write m plus n minus 2 is less than 1402, which is less than m plus n. Therefore, m plus n minus 2 is less than 1402, which is less than m plus n minus 1, which is less than m plus n. From here, we can deduce that m plus n minus 1 equals 1402. Adding 1 to both sides, we get m plus n equals 1403. And that's our final answer. The value of m plus n is 1403. To summarize what we did, we used the digit count property to set up inequalities for both numbers, multiplied these inequalities, simplified the product using the properties of exponents, and compared the exponents to find m plus n. Today we'll be looking at a special case where both the bases and the exponents are equal. Let's examine what happens when we multiply exponential expressions where both the bases and the exponents are the same. We'll look at two methods to approach this. First, let's use the product of powers rule. This rule states that when we multiply powers with the same base, we add the exponents. Alternatively, we can use a different approach. We know that a to the power m times a to the power m can be written as the product of times a all raised to the power m. Now, we know that a times is simply a squared, so we can rewrite this as a squared all raised to the power m. Both methods give us the same result. From the first method, we got a to the power 2m. From the second method, we got a squared to the power m. And we can show these are equivalent using the power of a power rule. So to summarize, when we multiply powers with the same base and the same exponents, we can write the result in two equivalent forms. First, we can write it as the base raised to double the exponent, or as the square of the base raised to the original exponent. These two forms are equivalent due to the rules of exponents. Let's finish with a concrete example to see both methods in action. Let's compute 2 to the power 3 times 2 to the power 3. Using the first method, we add the exponents. So we get 2 to the power 3 plus 3, which is 2 to the power 6. That equals 64. Using the second method, we first figure out what 2 squared is, which is 4. Then 4 to the power of 3 equals 64. As we can see, both methods give us the same result of 64. The key insight here is that when we multiply powers with the same base and the same exponent, we have two valid approaches that are mathematically equivalent. You can either add the exponents for the same base or square the base and keep the same exponent. Let's start with our first example. We need to find the value of a raised to the power of b plus 1 times a raised to the power of b plus 1. Let's solve this using two different methods. For the first method, we'll add the exponents when we multiply powers with the same base. Now, we simplify the expression in the exponent by adding b plus 1 and b plus 1. For the second method, we'll first multiply the bases, since they're the same, and then apply the exponent. Now, let's look at our second example. We need to find the value of 2 raised to the power of square root of 3 times 2 raised to the power of square root of 3. Again, let's solve this using our two methods. First, with the product of powers rule, we add the exponents when the bases are the same. Using the second method, we'll multiply the bases since they're the same, and then apply the exponent. As we can see, both methods give us the same result. For the first problem, the final answer is a squared to the power of b plus 1. The final answer is a squared to the power of b plus 1. For the second problem, the final answer is 4 to the power of square root of 3. These rules of exponents allow us to simplify expressions efficiently. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.